Hello, everyone. This is our last of the Beluga lessons. Um, Today we're going to be covering new methods that enable Beluga to solve the wide range of problems that it's able to solve, all on yeah on singular not singular but on single arcs. And yeah, let's to get started. I'm kind of going to go in order in the order I use these. But it's not super important, no way. But what we're going to actually start out is a method called index reduction. So traditionally, the optimal control law is found by solving the M algebraic equations given by the partial of the Hamiltonian with respect to u is equal to 0. So in all the all the different traditional optimal control lessons we did prior, we would get M equations and then solve explicitly for the control. So our control is defined by algebraic equations, not differential equations. But and then in addition, if there are multiple solutions to dHdu equal to 0, we choose the solution which minimizes h. And then this is the minimum principle that we learned on Wednesday. But that's not always possible during this kind of process. So if you in Beluga, and I'll show this later, if you select control method algebraic, it will do this. This kind of traditional solve algebraically for dHdu, and if there's multiple solutions, let's say there's a sign or something, it will go through the list of possible solutions and pick that which minimizes the Hamiltonian. But, and there's always a but, often an analytical solution to dHdu equal to 0 is not available. And this could happen, so for example, if dHdu turns out to be a transcendental equation, so that means it doesn't have a closed form solution, or if you have some problem that uses like a numerical table or something, or a numerical function that doesn't have any analytics to begin with. So it might seem that the response to that is to use a numerical solver, because we have numerical root solvers for functions. But those tend to be super slow. Not too slow where you can't use it for one solution, but they're slow to be using at every propagation step. So numerical root solver is too slow and is unreliable as well. So too slow and unreliable to do at each time step. Okay, so the way we get around this, and this actually comes through now Dr. Thomas Anthony's ICRM method that he did here at Purdue under Dr. Grant, but it's not the entire ICRM method. It's just the way he got. That method produces controls that you can't solve for analytically. So he kind of brought this in, which is a way to solve DA. Well, I'm getting ahead of myself. Let me just say this, that the system, so this system, let me change this. Let me say, yeah, this type of system is a semi-explicit differential algebraic system of equations, and then that's referred to is a abbreviated DAE, and it's of index 1. So the index refers to how it's actually the index refers to how many time, like how embedded algebraic equations are, and how many times you would have to differentiate those said algebraic equations to get all differential equations. So so let me just say it mathematically out. So we have our dynamics of the function. So this is the differential part, and then we have the algebraic part, which is our dHdu, and then you keep the kind of nomenclature. In this case, you can have some g, t, x, and u. Yeah, so one way to solve these outside of optimal control is the term index reduction. So the index 1 means that we have some algebraic equation there. If we have an index of 0, then it's all differential equations, then it's an ODE, and that's preferable because then we don't have to solve, we have no longer algebraic equations to solve. So the way it's done in this case, index reduction can turn the DAE of index 1 into a normal ODE, so ordinary differential equation. So the way, so it's actually kind of interesting the way we do this. So we take our differential equations here. So I'm going to use that notation with the underscore u. What we're going to do is take the derivative of this. So we get 0, and then on one side, and then kind of using the chain rule, well, ddt of dh du, and then now this is the chain rule here. So that's our time component. Now we get our state component here. And then we get a component with respect to the costates. And then we get a component with respect to the control. So what we ultimately want is u dot, right? And then that sits here. So we just do some algebra let me solve for u dot. I'm going to kind of clean this up by going back to the subscript notation. So HUT plus HUX x dot plus HU lambda dot plus HUU u dot. And then it depends on the way you're actually handling this. You can do some substitutions. So when we propagate, we're only going to compute f. So we can replace x dot with f. And yeah, so you could have this, and you're already going to compute lambda dot. But again, this too, so like you could get this in whatever form works the best. You could also pre-compute this is the partial of the Hamiltonian with respect to x, because that's what lambda dot is, the negative of that. But also HU lambda is also equal to, because H lambda is f. To also express it this way as well. They're all kind of equivalent, but ultimately we take this and then we just solve for u dot. So what we end up getting is that if we just bring u dot to this side and then multiply both sides by the negative inverse of h du. Yeah, so we have that, or say you store lambda dot already. You could save on some compute time if you do this then. Okay, so now in the BVP solver, because this treats the control is any other state, like as we do the states in the co-states. So as long as HUU is non-singular, because we have to import it, right? So as long as this is non-singular, solving for u dot is guaranteed. So unlike numerically solving for u, if you have a nonlinear equations, which is not, you don't get a guaranteed solution. In this case, as long as you can import HUU, then you're going to get a solution. Now, if HUU is poorly conditioned, your solution is not necessarily going to be great, but that kind of falls to everything else as well. This is a conditioning problem. So yeah, as I said already, we append u dot to the other differential variables, which are states and co-states. And then we also we need an additional boundary condition, because we just need a starting place to integrate from. Theoretically, you can add this to the end, but it just makes sense to add it to the beginning, particularly if you're using a shooting method. So we have our initial DHDU is equal to 0 at time t. Yeah, so this is super helpful. I actually use it more times than not because you don't have to worry about simply solving something analytically. It just makes life a bit easier, or a lot easier in some cases. So let me see. I was actually going to show an example of this.
This is this boundary condition. This is the partial derivative of h with respect to u at t0 is equal to 0.
Yeah. So it's actually, this process is very reminiscent of the way we dealt with state constraints, inequality, this state path constraints in the prior lesson, because we just, you're guaranteed to get u dot pop out, like as I showed, like u dot's going to come out, so you don't have to take multiple derivatives. But once you do that, once you have it in a differential form, which is like kind of what we're doing with the state constraints prior, once you have it in differential form, you have to impose the constraint at the beginning. But solving DHDU equal to 0 numerically is kind of built into the boundary variable, like the BVP solver, and it's happening simultaneously with everything else. It doesn't have to happen at every time step.
All right, thank you.
Yeah. So actually, I could pick almost most of these, and then they have, I guess I'll just show where it shows up. Yeah, most of these have differential control laws. So if I'm going to show this example later in this lesson, but if you look down here, this one's algebraic. Okay, this is the few ones that have an algebraic one. So it's actually a complex problem. So instead, let me, this one's interesting. This one, differential. So see how I specified it here in optim options. In the future, we might make it more explicit, but this is labeled differential. Just if I don't think anyone will, but in old versions, find this, because I think everyone's up to date on Beluga. In old versions of Beluga, it was also called ICOM or DAE, but those were misnomers. So we've changed it to differential, just because that's the way we're expressing it. And I don't think I need to run this because it's kind of all in the machinery that I showed in prior lessons. But that's how you specify it. Okay, so moving on. Now this is the next area. The next technique I'm going to cover is the uniform trigonometrization method, which from now on I'm just going to call UTM. And this is actually devised by Hittich, who's on this call. And so the way I'm going to present it here is going to be more or less how it's implemented in Beluga. So this is, well, let me just go with my notes instead of getting ahead of myself. As seen in the last lesson, applying inequality path constraints traditionally is a tedious and difficult process requiring prior knowledge of solution structure. Yeah, so the main thing is that we don't want to do all that stuff with multiple arcs and saying, when does this one come across? And the problem I showed at the end of last lecture, that was an easy path in karate path constraint problem. You can imagine if we're dealing with some aerospace vehicle with heat constraints and G-loading constraints and all the other possible things that could be there, you don't want to manually do any of that. So UTM modifies problems with inequality constraints so that they are solvable on a single arc. Sometimes it's called a phase. Single arcs without prior knowledge of arc ordering. So you don't even need to know, like, I have an unconstrained arc, a constrained arc, unconstrained. That's not needed for this. So there's two parts. There's a UTM. There's the part that handles control bounds, so bounds on control variables, and then there's a part that handles just like general state control constraints. I'm going to start out with the handling of control bounds. And then this is what's called the epsilon trig regularization method, but it's kind of was brought into UTM. So we have some U, and you can have multiple controls, so that's why I'm labeling it UI is less than or equal to. So UI is bounded by UI min and UI max. Here. So what we do is we replace the control UI with a, I'm going to put this in parentheses, pseudo control. I want to say util.i, which is placed within a bounded function. So there's a way you could, well, I'm going to show you how UTM does it, and then there was a paper that came out in SciTech that they actually generalizes this to like a lot of different bounded functions, but Beluga can't do that yet, so I'm just sticking to the UTM method. So I'll write it out. But the important thing is this sign here. So see how a pseudo control is within the sign function, so that whatever value it takes, the output can only ever be between 1 and -1, because the output of signs only ever between 1 and -1. And then you have this here. This scales the sign function, so instead of it scales between your min in max values with the offset to center it. So yeah, it's centered within your range. Oh, and that's also, I guess that's combined with the 1/2 too. So this means that your U min and U max don't have to be symmetric around 0. If it's symmetric around 0, you could actually eliminate the offset value. But yeah, so then that's yeah, so that's that. Okay. Yeah, I did summarize this. Is that this is only, so this function only outputs values between ui min and ui max. Yeah, so then once you substitute this in, then the solver can theoretically pick things and any solution that it comes up with that optimizes the problem like normally will be satisfy the constraints. The only thing that has to be taken into account is that the solver will still fail if bang bang control solutions exist. So particularly in cases where you have a linear controller, you get the bang bang solutions you saw last time. And this is because so those have the discontinuity in the control. And it's because of the integration. I guess I said the thing twice because I speak past myself. Handle discontinuities. So the solution to this, that we introduce a small error term to smooth the, I guess I go with solution. So in the case of the UTM, and I guess I meant to say to the path cost. So this is it in the normal UTM. We have the path cost L tilde, which is the original path cost plus a term for every control that we regularize in this way, which is just the cosine of the new pseudo control. So am I seeing one slide? I guess I'll proceed then. I don't know why it does this sometimes. Oh, here you go. So the zero term penalizes control changing too quickly. So that the solution is smooth. So the way this will look, this is a kind of a generic example, is that you have this is your control, and this is time. And say these are, you have your like control bounds here. I guess let me do that in black actually. So say our optimal solution looks something like this, and then there'll be a discontinuity here, and I'll draw a line that connects them to clarity, and then we have a discontinuity here. When we have different epsilons, the solution will actually look something like this. Is the extreme case of it. So it looks something like this. And then if we pick like a smaller epsilon, you get it closer. Because the error term will be smaller. So as you make this epsilon smaller here, the amount of error you add to the problem becomes smaller, but then the problem becomes more like numerically ill-conditioned. So there's a limit to what you can do. But so as epsilon goes to 0, the regularized problem approaches the original. Yeah, so the way you do this in, I don't have this in my notes, but I want to add it. So usually with continuation methods, start epsilon relatively high, then bring close to 0. So yeah, so when we do our continuations, it's easier to, because the problem is smoother in better conditions. When epsilon is bigger, it can't be too big because then you get kind of weirdness happening. But if it's relatively big, then the smoother problem is numerically easier to solve. And then only when you're like done and want the final solution. So at the end of your continuation process, then you bring epsilon close to 0. Just let me show that. And all the stuff I'm showing today is in the examples, the Beluga examples, so you should already have them if you have the Beluga repository. So I'm going to go, this is from a paper. I assume that it's referenced here, but this is a good example of using this kind of regularization. In Beluga, we specify here, so we add a path constraint, and then now the path constraint's on U. U has no units. There's a lower bound of U min and U max. Activator, that's what we labeled epsilon I, but you put in a constant. In this case, it starts as 1. And then in Beluga, this method's called epstrig. That might have to be clarified in the future. But that's from its kind of like original name before it was kind of made part of UTM. So if we solve this oscillator problem, should solve relatively quickly. Let me close these other things. Okay. And then plot it. This is, oh, you open? Oh, yeah, it is. I'm sorry. Okay, so here's the kind of the solution. It's a phase plot. It has two variables, x1 and x2. These blue ones are kind of, so if you look here, the last continuation step, well, I guess the first continuation step brings it to the solution, and then the next two series bring it from a high value to a low value. And so these blue solutions are when epsilon's big, and then we go to the red with this corner here where epsilon is small. And if you look at what the control does, so as I kind of sketched out, we have our bounds, and when epsilon's big, the control is pretty smooth. But as we bring in, the solution's non-optimal. I think this minimizes time. I should have checked beforehand. Yeah, so we minimize time. So you can see how the solution is non-optimal. But as we bring epsilon smaller, our final time becomes closer to the optimal value. And the red line approaches what we expect is this bang-bang control, where it goes from one boundary to the other. And you can see a little bit of error near the corner, like when it comes on, but that becomes really insignificant. So yeah, that's the control bounding part of UTM. Now we're going to go with the state bounding part. So and actually, some of the example problems in Beluga use this also for just control constraints. It depends on what you're doing, the specific problem. Sometimes this is just better numerically too. This doesn't have as many, like it's not, it just as a heads up, it's not as, what's the right word? Well, maybe I'll talk about that later, after I tell you what it is. So given a two-sided state path constraints of form. So UTM in its normal form deals with two-sided inequality constraints. So you have some f of t of x and u that's bounded between a min value and a max value. So the way we do this is we handle them with an interior penalty method. Yeah, so this is really just like the continuous optimal control version of what you would see in a parameter optimization course. So penalty function is added to the path cost. So we have some L tilde like before, and L. Instead of the error term, we add this for each of the constraints. We multiply it by the smoothing term as well, because it behaves in a very similar way. And then we have a sequence. I'll just write it out and then show you what it looks like. So this is min, max, min, max, min. So this if you remember from trig class, whenever the secant function, after when you input pi over 2 or negative pi over 2, it approaches infinity, and that's kind of the property we use. So this axis is actually SI, and this is going to be a UTM penalty. So this would be SI min and SI max. And then what this looks like is something like this. Oops. That's not good either. So it kind of goes up. Yeah, but it's symmetric, and the drawing's not great today. And then this is 1. This would be 1 if you're just looking at this penalty function. I actually prefer the way it's implemented in Beluga is I subtract the 1 out, so it kind of minimizes that really close, 2-0 actually, I think. It goes up to infinity on both sides. So, and then that's, yeah, but basically if we're in here, if we have a solution that resides in here, if it tries to push off to the boundaries, then it's going to, the cost is going to increase infinite, like it's just going to increase unbounded. So you always have some push off from the constraint, and it keeps your solution within the constraint boundaries, because in order to leave the constraint boundaries, it would add an infinite cost. I didn't say that super clear, but I think the idea is, if you've used penalty methods before, the idea is clear enough. So just reiterating, Beluga modifies the penalty function by subtracting 1, which from experience makes handling multiple constraints easier. Because, so if you don't do it, like, the 1 gets multiplied by the epsilon, so when you bring epsilon down low, it will disappear anyway. But when you're dealing with multiple constraints and you want to keep one epsilon high and one epsilon low, if you subtract that 1 off, it means you're not offsetting the cost by some like non-zero value, and it just makes kind of things easier to balance. But yeah, so I included that in a paper I wrote for last year's aviation. But yeah, it's not necessary, but it's so you know what Beluga is actually doing. So we have the same thing as before. Okay. And then you could extend this, say, or generalize it is probably the right word. So in principle, any reasonable penalty function may be used. So really, it just needs the property that as you approach the constraint, that it goes to infinity. So like you can do 1 over s for one-sided. Now I think there's better ones even for that, but for one-sided constraint. Or you can do what we do in Beluga because we only have the UTM. If you have only one-sided constraint, you just put the other side of the constraint far away where you don't deal with it. Like on the and then also yeah, I've released this was in the aviation paper I already mentioned that I wrote that this penalty method may also be applied to inequality boundary conditions. So you do the same thing, but instead of applying the constraints to the path cost, you apply it to the initial or terminal cost. But it's the same deal. So I'll quickly show where this is in. I don't even know if I pre-selected one, but it's they're only difficult to find when I'm looking for it. Type of constraints. Yeah. So this
Beluga functions are like your car keys.
Yeah, kind of. It's so this one uses UTM, but it uses it actually for the control. But see how it's specified as method UTM? Let me see. Oh, actually, I just did this one for fun. This one's not up there yet. But this is actually like a hanging chain problem, and I use UTM to specify. So we have, if I run this, yeah, I haven't pushed this yet. My computer, I think it's, yeah, okay, there we go. So I don't know why plotting is taking so long. So you can see if we have like a weighted rope or a hanging chain, these will be solutions for different lengths of chain. But I won't say it's hitting a table. So this would be the case if it's hitting the table. I use UTM. It's specified the same as the control constraints, but yeah, in this case we just specify UTM there. Let me plot that. And I had to use more solutions because of when you approach a constraint, it gets numerically unstable. So you can see a series of solutions, and the last one is like last blue one. That is, yeah, you can imagine if you hang a chain or a heavy rope on the floor or table that's right here, that's what it'll look like, and then yeah, that's the solution to that. Yeah, I actually did this problem, so I had a problem where the independent variable wasn't time. But yeah, that's that. So UTM is often is pretty there's kind of a trade-off to just have, because like I said, you can use UTM also for just simple control constraints. It depends on some problems that's actually numerically more stable, some problems it isn't. But it's always better than solving it using a multi-point boundary value problem, and I guess that's the main takeaway. The next method, and this one, this one was developed by, I'm going to mispronounce his last name. I practiced it before. Harish Saranistan. I knew him. Here it is. I apologize that I butchered his last name. So yeah, this is so we have the relaxed, autonomously switched hybrid system approach, which from now on abbreviated rashes, which yeah. So yeah, so inequality paths constraints are not the only thing that makes like multi-point boundary value problems and ones that are difficult. So, well, once again, I'm getting ahead of my notes. Difficult to solve multi-point boundary value problems. Also result, I could say, yeah, also result from quantities that have discontinuous switching. So I don't know. This probably is not the clearest way to say it, but I'm trying to fit it to the general way it's implemented in Beluga. In the original papers, it is stated as like dynamic set switch, but we applied it in a way where you could just have any quantity switch, whether that's in the cost. Well, the original paper also talked about switching in cost, but beyond just dynamics and cost, you could switch any quantity in Beluga using this method. So here we consider the quantity, I'm just going to call it QI, some quantity. It can be dependent on time, states, controls, and then that is either like the normal expression if some switching function g is less than 0, or it's 0. 0 doesn't depend on anything. It's 0 otherwise. And that's so yeah, so in Word that's where quantity QI is 0 if switching function GI is non-negative. So you can imagine we have some Q, right? And then this will be the switching, and it's want to be in this kind of two-dimensional way, but it's just a way to visualize it, like as a slice of what's happening. So this is GI, and so you have your quantity, it's just doing its thing until it reaches the switch, and then it'll drop to 0, and then nothing. So this is kind of could be defined as almost a unit step function. So I'm just going to say this is H, like for every side or whatever, H of GI. So you can think of it as 2i is equal to 1 minus h gi times this like raw quantity, whatever, whether it's a value or some function, it doesn't matter. So we replace the step function with a sigmoid function. So sigmoid, that's like one of those smooth S functions. To remove the discontinuity. So we take this, and then that is approximately equal to 1 over 1 plus e to the when I say gi over epsilon. In the original paper, it's a multiplicative term that when you bring to infinity, it'll approach like the original, but just for consistency in using epsilon as smoothing parameters, when we bring epsilon to 0, it's going to reach the original problem. And what this kind of looks like is if we have our original step function here, let me drop it down a line. Use blue. Right, and then, so yeah, this would be 0 and this would be gi, and this will be 1. What our approximation looks like depending on the value of epsilon. It's smoothed out like before, and this would be symmetric. I just did a terrible job drawing it. This. So you might think that there might not be many cases where you just want to switch a quantity off, but if you start combining these switching quantities together, you can model things like dropping a stage in a rocket launch, or that's actually where we've used it the most. But any kind of switching dynamics you can represent by piecing these together. So yeah, complex switching behavior can be achieved by combining the switching quantities together. So yeah, and now I'll show you a problem in which that's the case. If we go to BFG, which I think is based off of a SpaceX rocket design or something. If you look here, based on what stage the rocket's in, this is a multi-stage rocket, and the thrust, so you could define that as on the optimal control problem, you can define a switch, and this takes the quantity thrust. So every time that the thrust is in place, we'll actually switch it from this engine 1 function quantity to the engine 0 to engine 1. So switch between these, and the switches are when the mass crosses the threshold. So it switches engine 0 off when you cross this threshold. So when mass becomes larger than mass 0f, but then it switches this on, and we see we just negated that, so it's the opposite. when mass is greater than mass 0f. And there's a tolerance, and this is that epsilon again. And then we have the same thing with mass flow, because mass flow changes as well. I think with the recording, it makes Beluga slower for some reason. Yeah, so I think this is only one. Oh, this is a few, so it should go. Well, trust me that it's solved, and I didn't make up these plots because I have them. So you can see here, well, this is the trajectory, and this is the optimal control. But you can see how the switch between the masses, or at least the mass flow rate happens, and how there's this kind of like this continuous jump. I guess this isn't. I guess this is staging of engines. I should have looked more in depth on this, but basically, yeah, this uses rashes to get this kind of discontinuous jump between the different stages. And traditionally, you would have to solve a multi-point boundary value to have different states. Boundary power. You have to solve a multi-arc optimal control problem, which would result in a multi-point boundary value problem if you wanted to do this kind of thing like this. But in this case, we solved it in a single arc. And it's also nice because when you do it the traditional method, you have to kind of be able to solve a single arc and then introduce the second arc when it's long enough, and that makes continuation difficult. And the last thing I guess I'll cover here is some really brief notes on reduction using differential geometry. And this is the result of Mike Spirapani's work, and it's actually kind of, even though I've worked with him on a lot of this stuff, I'm not an expert, and it's kind of really deep math. But the machinery is in Beluga, so I just want to bring it up. Is that so differential geometry can use symmetries in the problem to reduce the number of variables that need to be propagated and sensitivities computed. So I guess a shorter way to even say that is that you can use differential geometry to give yourself a smaller problem, which is an obviously good thing. We call so what we remove, so I'm going to say that we remove states, and this is probably not precise enough, but states, so they could just be general parameters We call these quads, and that's because they are reconstructed using simple quadrature techniques. I guess I'm doing methods. If you can't tell, I'm not super confident talking about this area. And like I said, the machinery for that is in Beluga. My understanding of it is largely that, so the quads end up being things in which you can change the absolute value without changing the problem. So if you think of something like if you are solving a aerospace problem on a spherical Earth, and you have latitude and longitude, and you could picture that if the Earth is spherical, you could move the Earth underneath the plane, the problem, and the solution you get out, so the control law that you get out in the particular control profile would be exactly the same regardless of what latitude and longitude you start at, as long as the relative change in latitude and longitude are the same. So those kind of act as coordinates, and you could, if you could redefine the coordinates by offsetting them, those are more or less what quads are. So you could theoretically remove latitude and longitude from the problem when you're solving it, and reintroduce them, recompute them after the problem is solved, and saving then on computation time. So if we go, there's one problem in the examples that implements this, and this is actually a Beluga problem. If you're working on Beluga, you're going to see quads show up in the code. It's usually Q, but see, it's specified. So if you look here, we, in addition to solving everything else, we define symmetries. And what this is doing in the Beluga problem, there's a symmetry in X and Y, which is basically what I was saying about being able to move things around. So you can slide the Beluga problem on the XY plane. You could twist it on the XY plane. Ultimately, as long as the relative change in Y is the same, or like whatever that ends up being, then the problem's going to have the same result. It doesn't matter how you define X and Y. So that's what these symmetry variables are basically saying. And then in addition to that, so we also, so you could define symmetries, and then you could specify the method is diffeg, which is short for differential geometry, and then you could feed in the option to the optimizer that reduction is true. So that means it's going to reduce the problem. And if we run that, it should solve. It's unfortunately, and this factors into my own planned research, is that it's not any faster because the BVP solvers don't know how to handle them super well. But like always, you can trust that the solution. Looks like it should. So if you have more, if anyone has more interest in this, just let me know, and then I'll get you hooked up with the right things. But with that, that concludes the entire Beluga course. We of course welcome anyone who wants to help contribute to Beluga and use it in the research. And so thank you, everyone.